Hello and welcome to lecture number 21 in the course Computer Graphics. We are currently discussing the graphics pipeline, that is how the 3D scene gets converted to a 2D image on the computer screen. What are the stages there to perform this task? Together these stages are known as pipeline, as we have already discussed. So, let us just quickly have a relook at the pipeline stages and then we will start our discussion on today's topic. What are the pipeline stages? We have object representation as the first stage, then modeling transformation as the second stage, lighting or assigning color to objects as the third stage, viewing pipeline as the fourth stage, and scan conversion as the fifth stage. So, here I would like to re-emphasize on the point that this sequence that is shown here need not be exactly followed during implementation of the pipeline. There the stages may be in a slightly different sequence. Now, among these stages we have already discussed first stage, second stage, third stage, and currently we are discussing the fourth stage, that is viewing pipeline. As you can see here in the viewing pipeline there are sub stages. So, we have viewing transformation, clipping, hidden surface removal, projection transformation, and window to viewport transformation. Among them we have already discussed in the previous lectures. We have already discussed the viewing transformation, the projection transformation, and the window to viewport transformation. Two more operations in the fourth stage are remaining, namely clipping and hidden surface removal. So, these operations we are going to discuss in today's and subsequent lectures. So, in the viewing pipeline stage we have covered these three transformations: view transformation, projection transformation, and viewport transformation already, and there are two more operations, clipping and hidden surface removal, which are part of the fourth stage. So, these operations we are going to cover in the lectures that we are going to have this week. Let us start with clipping. What is this operation and how it is performed? If you may recollect, earlier we talked about a concept called view volume. So, essentially what we discussed is that when we are trying to generate a 2D image, essentially this is analogous to taking a photo of a 3D scene. So, we first perform view transformation to transfer that content from world coordinate system to view coordinate system. Then we perform projection transformation to project the 3D view coordinate system description of the scene to a 2D view plane description, and finally we perform window to viewport mapping. However, in this process what we project on the view plane? We project only the objects that are present in the view volume, that is a region in the 3D view coordinate space that we have decided to project. So, whatever objects are within the view volume should be projected. Thus, we need to define this view volume in this 3D region in the view coordinate system before projection. So, whichever object lies within this volume are projected, whereas objects that are outside the volume are discarded. For example, let us have a look at this figure. Here the view volume is shown with this rectangular parallel pipe. Now, as you can see, this object is entirely within the view volume. So, it will be projected on the view plane. This object is partially within the view volume. So, whichever part is within the view volume will be projected, and the outside part, this one, will be discarded. Whereas, in this case the entire object is outside the view volume. So, it will not be projected. So, we have three situations. In one case the entire object is within the volume. So, entire object is projected. In the other case object is partially within the volume. So, which part is within the volume will be projected, whereas the outside part will be discarded. And in the third case we have the entire object outside the volume which will be discarded. Now, the process of discarding objects is called clipping. So, before projection we should perform clipping, and then whatever objects remain should be projected. Now, the question is how a computer can discard or clip an object. That is done through some programs or algorithms which collectively are known as clipping algorithms. So, we perform clipping with the help of some clipping algorithms, and in this lecture and subsequent lectures we will go through few of those algorithms which are easier to understand. Before we start our discussion on the clipping algorithms, we should keep in mind 2 points. First thing is, the algorithms will be assuming that the clipping is done against canonical view volume. To recollect, a canonical view volume is a standardized view volume where the shape of the view volume is rectangular parallel pipe and its bounding planes are within a fixed range. So, it is a standardized view volume. So, whenever we are talking of clipping, we assume that the scene is already transferred to the canonical view volume, and then we are performing clipping. Secondly, we will first discuss 2D clipping algorithms. For simplicity, it will be easier to understand clipping when we are dealing with 2D objects, and then we will extend our discussion to 3D clipping. So, let us see what are the algorithms that we can use to perform 2D clipping. Now, since we are discussing 2D clipping, we have to restrict ourselves to the 2D concepts. Now, view volume that we mentioned earlier is a 3D concept, but that is not relevant in 2D. So, instead of view volume, we now use the concept of view window, which is a square region on the view plane. In earlier lectures, we already got introduced to idea that we mentioned that on the view plane there is a clipping window on which objects are projected. The concept is same as the view window. So, it is equivalent actually to assume that the view volume and all objects are already projected on the view plane. That is another way of looking at 2D clipping. So, already projection is done and we have 2D clipping window. Now, we want to perform clipping. So, that is after projection we want to perform clipping. So, this view volume is projected to form the window and other objects are projected to form points, lines and fill areas such as a polygon. So, we have a window which is formed by projecting the view volume on the view plane, and then other objects are projected to form points, lines as well as fill areas such as polygons. So, then our objective boils down to performing the clipping operation for points, lines and fill areas with respect to the window. So, the scenario is that we have a clipping window or view window and we have objects that are projected on the view plane and we want to clip the projected objects against this window, where the projection takes place in the form of points, lines or fill areas. Let us start with the simplest of all clipping, that is point clipping. How to clip a point against the view window. Let us assume that we are given a point with a coordinate x y. Now, the clipping idea is simple. We have to check whether the point is within the window or outside. So, what we have to do, we simply have to check if the coordinate values lies within the window boundary. So, we need to perform these checkings. So, here we are checking the x value against the window boundaries and y value here we are checking against the window boundaries to determine whether they are inside the boundary or outside. So, if it is inside the boundary we keep the point, otherwise we clip it out. That is a very simple idea. More complicated is line clipping. Here we do not have a single point, we have a large number of points to consider. So, the corresponding algorithm would be more complicated than what we have seen for point clipping. Let us first talk about a very simple intuitive approach. What we can do? We can represent any line segment with its endpoints and then we check the endpoint positions to decide whether to clip or not. So, we are representing a line with its endpoints, then for each endpoint we are applying this point clipping approach to check whether the endpoint is within the boundary or not, and after checking both the endpoints we can come to a conclusion whether the line is within the window or not. But there is a problem. If we follow this approach, there can be either of the three scenarios. In the first case, both endpoints may lie within the window boundary. Consider this line segment L1. Here both the endpoints are within the boundary, so we do not clip. In the second case, one endpoint is inside and the other endpoint is outside. Consider L2. Here this endpoint is inside and this endpoint is outside. So, in that case it has to be clipped. And then there is a third scenario where both the endpoints are outside. However, here we have a problem. Consider the line L4. In this case, both the endpoints are outside and the entire line is outside. So, we can simply discard it. But in case of L3, here also both the endpoints are outside. However, a portion of it defined between these two intersection points is actually inside the view window. So, we cannot discard the line entirely. Instead, we have to clip out these outside parts and discard them, whereas this inside part must be kept. So, in this case then we have to check for line boundary intersections to determine whether some portion is inside the window or not. Now, this intersection checks are computationally expensive because they involve floating point operations, and in practical applications every change of screen involves large number of such intersection checks, which may slow down the overall rendering process, and it may even turn out to be impractical. So, we require some alternative, some better solution. One such solution is provided by one algorithm called Cohen-Sutherland algorithm. Let us go through the steps of the algorithm. So, in this algorithm we assume a representation of the view plane. So, here we assume that the window and its surrounding is divided into 9 regions as shown here. So, this is the window, the central part, and then we have above left, above right with respect to the window, left, right with respect to the window again, and below left, below and below right with respect to the window position again. So, these 9 regions are assumed to represent the view plane, and how we get the 9 region? By extending the window boundaries as shown here. So, this is the first assumption. Then what we do? We assign a code to each of these regions. Now, there are 9 regions, so we require 4 bits to represent all the 9 regions, which is very obvious, and each region is given a unique code, a 4-bit unique code. Now, each bit indicates the position of the region with respect to the window. So, this is the 9 region representation, and this is the codes assigned to these 9 regions. Note here that each code is unique. So, above left is represented by 1001, above is represented by 1000, above right is represented by 1010, left represented by 0001, right represented by 0010, below left represented by 0101, below represented by 0100, and below right represented by 0110. The central region or the window is represented by all zeros, and the organization of the code looks something like this, where the leftmost bit indicates above location, next bit indicates below location, next bit indicates right, and the rightmost bit indicates left location. So, each location can take either 1 or 0. 1 means it is above, 0 means it is below. For example, consider 1001. So, we have above 1, below 0, right 0 and left 1. That means the region is above left as shown here, because these 2 bits are 1, whereas below and right bits are 0. So, that is how the codes are assigned to each region. Now, that is the assumption and assignment of code. Then the algorithm starts working once those things are done. So, in step 1 of the algorithm, we assign region codes to the end points of the line segment. So, given a line segment, we first have to assign its end points the corresponding region codes. How we can do that? Assume that the endpoint, one endpoint is denoted by P x y and the window is specified by these boundary values x min, x max, y min, y max. So, these are the boundary values which specifies the window. Then what we do? We perform a simple check to determine the region code of the endpoint P. What are those checks? So, we check the sign of the difference between y and y max. P has coordinate x and y, and x max, y max, x min, y min are the window boundaries. So, we take the difference of y and y max and check its sign. Now, the sign of this quantity will give us a result 1 if this quantity is positive, otherwise it is 0 in case of negative. So, we do that for each bit position. So, for bit 3 we check the difference between y and y max, for bit 2 we check the difference between y min and y, for bit 1 we check the difference between x and x max, and for bit 0 we check the difference between x min and x and take their sign, and then apply this rule to get the actual bit value. So, the first step is assignment of region codes to the endpoints. In step 2, we perform more checks on the region codes that are assigned to the endpoints, and then we take action. So, if both endpoint codes turn out to be 0 0 0 0, that means the line is completely inside. So, we retain the line. Now, if logical AND or the bitwise AND operation on the endpoint codes turn out to be not equal to 0 0 0 0, then the line is completely outside and we discard the entire line. Note that here we do not need to check for intersection. In the next step, when none of the cases that we just discussed in step 2 occur, we know that the line is partially inside the window and we need to clip it. So, in step 2 we perform checks to decide whether the line is completely inside or completely outside, and accordingly we take step. Then if none of these conditions satisfy, that means the line is partially inside and we need to clip it. That we do in step 3. So, for clipping we need to calculate the boundary and line intersection point. So, here we cannot avoid calculation of the intersections points, and that we can do in different ways. One possible way can be take the boundaries in a particular order. For example, first above boundary, then below boundary, then right boundary, then left boundary, and so on. Any order is fine. And for each boundary, we compare the corresponding bit values of endpoint region codes to decide whether the line is crossing the boundary or not. If the region codes are not same, then the line intersects that particular boundary, then we form the line equation from the endpoints and determine the intersection point by solving the equations, and then we assign region code to the intersection point as we have done earlier, and we do it for all boundaries, and in this process we discard the line segment that lies outside the window. Now, we have a new region code, that is the intersection point and the other endpoint with respect to a particular boundary. So, we compare the two new endpoints to see if they are completely inside the window. If they are, then of course, we keep that. If not, then we take the other endpoint and repeat the process. So, what we do in step 3? In step 3, we go for clipping the line. We start with one endpoint, assign region code which is already there. We check the region code with respect to all the boundaries following a particular sequence, and based on that check we determine if the line is intersecting a particular boundary. If that is so, then we use the line equations and the boundary equations to solve for the intersection point. Then we assign a new code the way we did before to this intersection point, and the intersection point and the end point clearly lies outside the clipping window and we discard it. Then we have two new endpoints, that is the intersection point and the original remaining endpoint. We check if it is completely inside the window. If it is, then we keep it, otherwise we repeat the process again for the other endpoint. Let us try to understand whatever we have discussed so far in terms of some examples. So, earlier we have shown how to assign the region codes, and based on that how to determine whether to clip a line or not. Let us consider this line segment defined between the endpoints A and B, and the window extents are provided here. The x min is 2, x max is 4, y min is 2 and y max is 4. We check the sign and accordingly we assign region code to the endpoints. For example, for A, let us try to do this. Let us start with bit 3. Here the corresponding expression is sign of 3 minus 4, which is sign of minus 1, since it is a negative quantity. So, bit 3 will be 0. Similarly, bit 2 again negative quantity, so it will be 0. Bit 1, this is a positive quantity 1, so it will yield 1, and bit 0, which is again a negative quantity, and we are taking the sign of it, so it will result in 0. So, our region code will be given by these bits or 0 0 1 0. In a similar way, we can check for B, which is 0 0 1 0. It will be same. Now, we go to step 2, series of checks. So, first check is whether both endpoints are equal to 0. Now, they are not 0 0 0 0. So, first check fails. Second check is if their logical AND is not equal to 0 0 0 0, which happens to be true in this case, So, we can be sure that this line is completely outside the window boundary. So, no further check is required and we can simply discard it. So, this particular line will be completely discarded just by checking the region codes. We managed to determine that it is completely outside. Now, let us consider another line segment that is given by the endpoints P and Q. As usual, we will first determine the endpoint region codes. The P code will turn out to be 0000, as you can see here. For bit 3, sign of a negative quantity 0, again bit 2 negative quantity 0, bit 1 negative quantity 0 and bit 0 sign of a negative quantity again 0. Similarly, we can determine the region code of Q, which turns out to be 0010. You can try yourself. Then once the region codes are decided, we go for the series of checks. First check fails, the endpoints, both endpoints are not 0000. Second check also fails, logical AND turns out to be 0000. So, it is not completely outside. So, we need to go for the third step and need to determine the intersections. From the endpoints, we can derive the line equation as shown here, and then we check for intersection of this line with boundaries in the following order. Above boundary first we will check with, then below boundary, then right boundary and then left boundary. So, for above boundary you can see that bit 3, which represents the above boundary of P and Q, both the endpoints are same. So, the line does not cross above boundary. Similarly, you can see that the line does not cross below boundary. There is a difference of the bit values in case of bit 1, these values are different. So, we can conclude that the line crosses the right boundary. So, we have to find out the intersection point with the right boundary. Now, right boundary line equation is x equal to 4, as you can see here, and we put this value in the line equation to get the intersection point at 4 5/2. This is the intersection point. Now, as you can see, let us call this Q dash. So, since the line crossed the boundary, so Q dash Q is outside the boundary because Q is outside. So, this segment is discarded and the new line segment becomes P Q dash. These are the two new endpoints. Next, we determine the region code of Q dash, as we have seen earlier, which turns out to be 0000. Now, as you can see, both P and Q dash have the same region code 0000. So, this segment is entirely within the window and it is retained by changing Q to Q dash. One thing was left earlier, we checked for above, below, right boundary, we did not check for left boundary. However, as we can see with this region codes of P and Q dash, because that is the new line segment, bit 0 is same for both endpoints. So, there is no intersection, and so at the end of the algorithm we get PQ dash as the clipped line. So, that is how we can check for clipping following this algorithm. Let us see one more example. Now, let us consider a slightly more complicated line segment given by M and N. As before, we can determine the region code as shown here for both the endpoints M and N, which turns out to be for M it is 0001 and for N it is 0010. Then in next step we go for the checks, series of checks. Here also first check fails, both endpoints are not equal to 0000. Second check also fails, logical AND results in 0000. So, it is not 0000. So, second check fails. Thus, we cannot completely keep it or completely discard it. So, there must be some intersection and we have to determine that intersection and clip the line. So, we need to determine line boundary intersection points and clip it. For that we need to decide the line equation from its endpoints, which is easy as shown here. Then we check for the line intersection with boundaries and following this order above, below, right and left boundaries. So, bit 3 of M and N are same, that means line does not cross above boundary. Similarly, it does not cross below boundary, bit 2 is same. However, bit 1 are different and the line crosses right boundary. Then we check for intersection points. So, the right boundary equation is x equal to 4. So, using this equation and the line equation we get the intersection point to be n dashed 4 9 by 4, that is here. Now, this point is the intersection point between the right boundary and the line, and since n is outside the right boundary, so as before we discard this segment n dashed n, and the new line segment becomes M n dashed. So, this part. Then we decide the region code of the new endpoint n dashed, which is 0000. Thus, we now have two new endpoints M and n dashed. M has code 0001 and n dashed has code 0000. Now, earlier we checked for above, below and right boundary, left boundary check was pending. We will do that next. Here if we check, we can see that for the left boundary the bit values are not same. That means again there is an intersection with the left boundary, and we check for that intersection points between the left boundary and the new line segment given by the endpoints M and n dashed. Now, we know left boundary equation is equal to 2. We use this equation and the line equation to get the intersection point M dashed, which is 2 and 11 by 4 here. Now, the point M is outside the left boundary, that we already know, that means on the left side. So, we discard this segment m dash, and new line segment becomes m dash n dash between these 2 points. This is m dash and this one is n dash. So, we now decide or determine the region code of this new endpoint m dash, which is 0 0 0 0. Then we go for checking the endpoint region codes again, step 2 of the algorithm, and we find that m dash and n dash have same region code 0 0 0 0. That means, this entire line segment m dash and n dash is within the window. So, the algorithm resets the line segment to m dash n dash, and we have already checked for all the boundaries. So, no more boundary remains to be checked, and the algorithm returns this line segment as the clipped line segment and stops. That is how the algorithm works. So, to summarize, the Cohen-Sutherland algorithm is designed to reduce intersection calculations. If we go for intuitive method, then when the line is completely inside or completely outside, it is difficult to tell. So, for every line we have to go for intersection checks. That is not required in case of Cohen-Sutherland method. Here we assign some region codes to the line endpoints, and based on the region codes we can decide whether the line is completely inside or completely outside. In those cases we do not need to go for intersection checking. However, if the line is not completely inside or completely outside, we know that there is some intersection and we need to clip. There we have to go for some intersection checks and find out the intersection points. So, some amount of intersection calculation still remains. But it reduces the calculation to a great extent, which is beneficial to render complex scenes faster, but as I said, it still retains some intersection calculations. So, this particular algorithm works well when the number of lines which can be clipped without further processing is large compared to the size of the input set of lines. So, when the number of lines that can be clipped without further processing is large, then clearly Cohen-Sutherland works much better, because no intersection calculation is involved. But if that is not so, then it still has some problem. There are in fact other faster methods that are developed to reduce intersection calculation further, and those methods are developed based on more efficient tests which do not require intersection or complex floating point operations. There was one algorithm proposed by Cyrus and Beck, which was among the earliest attempts in this direction, and which relied on parametric line equations. Later, a more efficient version was proposed by Liang and Barsky. However, in this course, we will not discuss those algorithms any further. If you are interested, then you may refer to the reading material that will be mentioned next. So, to summarize, today we have learned about clipping in 2D. Clipping means discarding objects that are outside the view volume. In case of 2D clipping, we want to discard lines or points that are outside the clipping window. Later on we will see how to discard fill area also that are outside clipping window. And in order to do that, we rely on some algorithms to reduce extensive intersection point calculations. One such algorithm we have learned today, that is Cohen-Sutherland algorithm. It is quite efficient, however, it still retains some amount of complex calculations which can be alleviated with other more efficient algorithms, namely by Cyrus and Beck or by Liang and Barsky. So, those algorithms we have not discussed. If you want to learn about those, you may refer to the reading material.